Now you can see that this zero-order hold output has these steps in them. Each one of these sharp transitions has frequency content that goes from minus infinity to infinity. So there'll be unbounded frequency content here. So instead of having a nice band-limited spectrum in the output, I'll get something that's not band-limited. What do you think the frequency response g of omega looks like for g of t? Well, if I've got a square pulse in the time domain, then g of omega is going to be a sinc. So instead of having this nice band-limited output, let's write down what g of omega is in this case. G zero-order hold of omega is the integral from 0 to t of e to the minus j omega t dt. So that's what? It's 1 over minus jt times e to the minus j, 1 over minus j omega times e to the minus j omega t minus 1, which is e to the minus j omega t over 2 times e to the j omega t over 2 minus e to the minus j omega t over 2. I've taken this minus sign and I've moved the minus sign to the numerator so I could switch the order here. It's divided by j omega. So now this is equal to e to the minus j omega t over 2 times 2j sine omega t over 2 divided by omega. Let's do that again. Oh, we've got some more room. Let the integral from 0 to t, e to the minus j omega t dt. So that gives us minus 1 over j omega times e to the minus j omega t minus 1. So that's 1 minus e to the minus j omega t over j omega. So the numerator is now going to give us e to the minus j omega t over 2 times e to the j omega t over 2 minus e to the minus j omega t over 2 over j omega. So that's e to the minus j omega t over 2 times 2j sine omega t over 2 over j omega. The j's cancel. I'm going to put the over 2 down here. So that gives me e to the minus j omega t over 2 times sine omega t over 2 over omega. Now I'm going to write this omega t over 2, and I'll put a t. So it looks like a sinc of omega t over 2 scaled by capital T. So when omega equals 0, this has value magnitude capital T. And outside of there, it's going to be a sinc function. So whereas before I have, recall I've got my y sub d of omega, which has, y sub s of omega, which has copies every 2 pi over capital T after I changed the time axis by capital T. This is pi over t minus pi over t, and I add height 1 over t. When I multiply by this expression, this e to the minus j omega t over 2 gives rise to a delay in the output by t over 2 seconds. So the output will be delayed by t over 2 seconds. We'll talk about in just a minute how I can get rid of that delay. Now what does the sinc look like? When omega equals 0, the sink takes on value 1, but I've got this capital T that scales it, so that knocks out my T here. So it takes on value capital T at omega equals 0. Now where's the first zero crossing of sine omega t over 2? I need omega t over 2 to equal pi, so I need 2 pi over t is equal to omega. So the first zero crossing happens here. So I have a sinc function that comes down and then goes back over and down and back over. So this is my g of omega for zero order hold. So the output of my ideal D to A converter would have gotten rid of these images, but now they're going to be suppressed.